Very much. Then today we're going to see it's the second lecture. It's the same idea like yesterday, but today we will apply the theory to parabolic PDE. Our constraint will be a parabolic PDE inside of an elliptic PDE that we showed yesterday. Then let's first just review a little bit, to recall what is the fractional Laplace, and then we will formulate our problem. And like yesterday, we prove the well-posed net of the state equation, and then we do the optimal control problem. Then as we defined yesterday, then the fractional Laplace operator that we defined by using the singular integral, then that is only the principal value of this integral, like what we clarified yesterday or how it's been. Then that's what we mean by the fractional Laplace operator. And the constant is given by this explicit formula. Here, gamma is always the Euler gamma function. Then the Sobolev space that we also use is also the space Hs of omega. Then U is in L2 such that this semi-norm is finite. But let me recall you that when we say that S is between 0 and 1, here is not a restriction, because if S is greater than 1, you have to change the definition because this semi-norm cannot be finite if S is greater than or equal to 1 unless U is a constant. Then if U is greater than 1, you just have to change the definition. You write S, if S is greater than 1, you write 1 plus delta, and you change by changing U to be the gradient. Then, so is that. Then here, taking S between 0 and 1 is not, it's how you define the spaces. Then the most important space, again, is the Hs0, that U is in Hs of Rn, and U is 0 outside omega. And we also denote by the dual of Hs0 by H minus S, such that we have the Gelfand triplet, which means that Hs0 is embedded in L2, and L2 is embedded in H minus S, and all those two embeddings are continuous and dense embeddings. Then that is so far the spaces that we have, and the fractional Laplacian that we discussed yesterday. Now we also need the integration by parts formula that we see yesterday, that here is, I want to integrate V minus delta S of U, but the condition that I need that U is in Hs of Rn and minus delta S of U is in L2. Then I integrate, I have here the energy form. Like we said, the energy, we just need information on R2n minus the complement of omega squared. We don't need information on the complement times omega complement times omega complement. We don't need to have any information on that. Then we have that minus the integral on the complement of V times the non-local normal derivative. Then that is the integration by parts formula for the fractional Laplace operator that we will also use. But if uv is in Hs0 of omega, of course at that time U is 0 outside omega and V is 0 outside omega, then this double integral is the same like integrating on all Rn. Now we can formulate our control problem here, that is the parabolic one. Then we want to minimize this functional. G of U is exactly the same like yesterday, but now the functional is defined on the space. Our U sub D will be L2 of the cylinder, which means 0t times omega, and our control space will be L2 of sigma, and the sigma is 0t times the complement of omega. Then we minimize this functional, and under the condition that our function U solve this parabolic type equation. Then here we have the equation is 0 in Q and U is Z outside. While we put here a 0 initial condition, we can put U0, but it doesn't change too much in the control problem. Then we said yesterday for the elliptic problem, here we have an exterior control, because if you see here, we have an exterior control, U is Z outside. Why is that? Even if I didn't say yesterday, because boundary control does not make sense for the fractional Laplace operator is due to the fact that Dirichlet problem is not well posed. If you give a function, you know the function of the boundary, you cannot recover. I can even put f is 0. You cannot recover an S-harmonic function just knowing the function of the boundary. Then the Dirichlet problem is not well posed. Then if this Dirichlet problem is not well posed, of course, the associated parabolic problem will not be well posed. Then you cannot have a boundary control. Then what we know, the well posed problem is that if I know a function g outside, I can recover an S-harmonic function. And that is the well posed Dirichlet problem for the fractional Laplacian is given in this way. Then for that reason, in our parabolic or elliptic problem, we just have an exterior control inside of having a boundary control. Okay? You know, for the classical Laplace operator, for elliptic or parabolic, we just have the boundary conditions. And here we have to have an exterior condition. And if you have any question, you can always stop me. Then here, first, let's see, then our state equation here is we want to find the function u in L2 of Q solving this state equation. This means have ut plus minus delta S, u is f in Q, and u is z in sigma. Then to solve, we will consider three cases for this. We will consider first the case where z is 0, that is very easy to solve. The second one, we will consider g is smooth. That will be also easy to solve. And the third one that is relevant for us is to take z in the space where we want to, the space of control, the space of control function, which means L2 of sigma. Then the third one will be difficult, we have to have other notion of solution, but the first two will be relatively easy and well know how to solve this type of parabolic equation. Then let's go to the first one. The first one, we have this parabolic equation that we have the equation it's f in Q. The function is 0 on 0t times sigma, and we put a 0 initial condition. Then if you know, we can here, since we have w is 0 outside, we can rewrite this problem as this abstract Cauchy problem, which means dtw plus minus delta s dw is f. What is this operator? This operator is what I mean, the realization of the fractional Laplacian with the 0 Dirichlet exterior conditions. What does it mean? That means that the domain of the operator is all u in hs0 of omega, such that minus delta su is in L2 of omega. Then if we define this operator, so then we can transform this parabolic system to an abstract Cauchy problem. Why we do that? Because we know easily how to solve a parabolic, a Cauchy problem. We have all the tools to solve a Cauchy problem. Then let's see what is the solution of that Cauchy problem. Yeah.
The W in the second equation 3.2, W is 0 in Rn or only in omega?
It's only in omega.
So what happens outside at time 0?
Yes.
Doesn't matter?
W here is 0 outside.
Okay.
Yeah. Because remember here, you have to be careful here, because the abstract Cauchy problem, you do not see it like it, because I have an operator A with domain that is in L2, then the condition is only in L2. Okay? And the operator, you have to be careful how it's defined. Here we defined it so, but we want to use semi-group theory that the domain of the operator must be continuously injected in L2. Okay, that's why for the fractional Laplacian there are a lot of results there that is not well written on those in this stuff, because you want to take if you take the space Hs of Rn, so you cannot say that you will lose the injection somewhere, and you cannot use the semi-group theory in this case. Then to notice that this operator here that we have here, we can just remind that this operator, you can also define it in another way. You can see it that it's the self-adjoint operator on L2 that is associated to this bilinear symmetric form. The form is bilinear, is symmetric, is continuous, is even coexistive. But how you have that? If you have a bilinear, symmetric, and continuous form, because the form will be closed, then you define that you have an operator. There is a one-to-one connection with this form with an operator, and you just define here. The operator is defined like U in Hs0 of omega, that there exists f in L2, such that epsilon a, the bilinear form is the integral of fv for all v in the domain of the form. And you define the operator at u is equal to your function f. Okay, but one can use, using integration by part and other tools, you can prove that defining this way is exactly what I gave here. But like I said, for Dirichlet's work, because one can prove that usually for the classical one, the Laplace operator, because this definition gives you a weak solution. Then you have to prove that weak solution is a strong solution, in the sense that the first equation is satisfied pointwise. That is the problem. But for the Dirichlet case, one can prove that the weak solution is a strong solution. But for other boundary conditions, if you see, nobody knows if a weak solution is a strong solution only for f in L2. If f is nice, you can prove that the equation is satisfied pointwise, but only L2 is not enough. I think the L infinity is enough. Then that's what we have. Then the operator minus delta S has a very nice property because it has a discrete spectrum, and the spectrum is only with eigenvalue that satisfy these inequalities, and the limit is infinity. But this is only proved because we know that the injection of H10 to L2 is compact. Then this means that the operator, what we have as a compact resolvent. Then if we denote by phi n, we can denote the normalized eigenfunction. Then one can also prove that the operator minus delta SD generates a strongly continuous semigroup on L2. Then by a strongly continuous semigroup, a semigroup is only an operator, a family of operator T, such that T of T is a linear and continuous operator from L2 to L2, and satisfy the semigroup property. As you know, the semigroup property is that what we know that T of small t plus S is T of T, T of S, and the strong continuity is that T of 0 must be the identity. That is the strong continuity, okay? Then that is what we call a strongly continuous semigroup. Then one can also prove that, using thing, you can prove that the semigroup is rarely given exactly by this formula. Okay, you can use the eigenfunction and the eigenvalues, and the semigroup is given by this series. Then if you know that you have a semigroup, then the function u given by exponential of minus t, which means the semigroup applied at u0, that is the unique strong solution of the abstract Cauchy problem. Okay, yeah.
Dr. Warma, for the first bullet, I'm wondering, have people already knowing whether lambda 1 can be lambda 2, the simplicity of eigenvalues? Have people already proven or disproven lambda 1 can or cannot be lambda 2 and so on or not?
We have finite multiplicity, but you cannot always say that always what you mean that, well, I cannot say, I know first that lambda 1 is not 0. That is clear.
Yeah,
that's come from the coexivity of the form. Okay? Then you say that lambda 1 cannot be lambda 2. What is, I can not say directly that lambda 1 cannot be equal to lambda 2. What I know that each lambda n has a finite multiplicity.
Okay, yeah. So I'm still working on this. I'm not sure whether this has been done or not. So I'm just curious if you know any existing results or not. So for if for one dimension, it's already clear, right?
In one dimension, you have the formula, but it's not an explicit. You have the asymptotic formula of the eigenvalues. I will give it tomorrow.
Okay. Yes.
I have the asymptotic formula of the eigenvalues that in one dimension.
Oh, the explicit formula?
Asymptotics. I have a formula plus a big K of K, okay?
Okay.
Lambda K is a something plus a big K, a big O of K. I will give it tomorrow, you will see. In one dimension, but after that you can't, because even in one dimension it's complicated, you cannot compute the eigenvalue like we are doing for the Laplace operator.
Nice. Yeah. Can we go back to one previous slide? One more. Yeah, this. So here, for this equation, before the last bullet,
yeah.
Do you know the structure of solution U? I'm wondering. I know you mentioned that it's very difficult. I agree. So the U.
U is in H10.
Yeah. Then to solve the equation below.
This where?
Yeah.
Here.
Can we solve U explicitly in terms of F in closed form?
No, U is only the resolvent applied to F, because that is this operator is invertible. Then U is the resolvent applied to F. That's the only thing you can say. If we say minus delta S D power minus 1 applied to F, that is U.
Oh yeah, formally that's good.
Why? Yes, you can give all the property that you want. I know I can study the regularity of U in this sense. But if you want to write it in a theory, you can write it, but it doesn't help, okay? Because you know the property of the resolvent. It helps a lot to have all the property of the solution U. Okay?
Okay, thank you.
Yeah. Then like what we say here, then the operator also, one can see that, like I say, one can also define this operator inside of defining an operator on L2. You can see it as an operator that maps HS0 into its dual. And in this sense, the duality map is given by that is equal to the bilinear form. Then in this sense also you have that minus this operator also generates a strongly continuous semigroup on the dual space. Then in this case, you can also solve the Cauchy problem by taking U sub 0 in the dual space. Then it's only given by the semigroup applied to U0. Then this means that our Cauchy problem, you can solve it if F is in L2 or if F is in the dual space, depending on which kind of solution you want. Now we want to see the other case, but I will use this notation that function that is in for a Banach space X, function that is in H10 of 0t with value in X, and that is 0 at 0, and the other one is 0 at t. Okay, and I will make the intersection with L2, so you do not U sub 0, and U is only the intersection with L2 that is defined on all HS of Rn. Now, if we let F to be in L2 of minus with value in the dual, if I say a function W in U0 is a weak solution of 3-1, remember that 3-1 is what we have with F. It's only that we integrate and you make the duality map plus the bilinear form is equal to here the duality map, that this equality hold for all v in HS0 and for almost every t. You don't need to test with function that depend on t. It's enough to test with function that does not depend on t. Then if this equality hold, we say that W is a weak solution. And remember that that is the bilinear form, that's what we have here, which means the energy form. Then you can always define weak solution by that. If you want, you can also integrate in t. In this case, you can test with functions that depend on t, but one can prove that the two definitions are equivalent. Then for simplicity, you can just test this with function that does not depend on t. Then we have existence. Then if you give me any function that is in L2 with value in the dual, then we have a unique weak solution, and it's only given by, that is here the integral of 0 of t, the semigroup with applied to the function f. We are making the convolution of the semigroup with the function f. That is only done, by using semigroup theory and the variation of constant parameter. That is only that you get this formula. If you didn't take u0 is 0, you will have the semigroup s of t times u0 plus this one. Okay? And also one can prove the continuous dependence of the solution to the data f, that the norm of w is always less than the constant times the norm of f in L2 of 0t with value in the dual. Then we always have continuous dependence of solution with respect to the given data. Like I said, this follows from semigroup theory and the formula of variation of parameter. It's like, what we are solving, the classical case here, I want to solve u prime is AU plus F. That's what we do in the first course in undergrad, the ODE. Then you solve the homogeneous part, and then you make the variation parameter to have the full spectrum. That is only that. Yeah. But we have to know that, the semigroup theory is only come from the so-called the Cauchy functional equation, because if you know the Cauchy functional equation, Cauchy say that if a function u satisfies the Cauchy functional equation and is continuous, the only solution is the exponential, and continuity already implies differentiability. Okay? That's why if you see a solution that is an exponential, that is only a first order equation. You cannot have anything else. That is the Cauchy functional equation. Okay, now we mentioned the following fact that we call the weak solution belong to here. But a well-known Lyon's theorem shows that this space is here. If we take L2 with this space HS0 and H1 in 0 to with value in the dual, then functions are continuous on the closed interval 0t with value in L2. You have this continuous embedding such that the initial condition makes sense. You can calculate u of 0, u of t, and that makes sense because solutions are already continuous on the closed interval 0t. But even if the right-hand side is in L2, we can even have more that solution is even continuous with value in the domain of the operator, and there H1 with value in L2. We can really improve the regularity if the right-hand side is a little bit smooth. Then in this case, we can even say here that we have a strong solution. Okay, this means that the first equation that we have is satisfies pointwise. This means for almost every t and almost every x in omega. Now, let's see the second case where we give a higher regularity, but we have a non-homogeneous exterior term. We assume that the non-homogeneity is at least it's H1 with value in HS of the complement, then I can always have an extension like yesterday we did to be in H1 with value in HS of Rn, such that the restriction is equal to Z. Then I have a function here, because I have a smooth domain, I can have an extension, that's what we call have an extension operator, and you can extend it to be in the full space, and the extension operator is even continuous. Then in this case, we say that we have a weak solution if U minus the extension is in U0. Remember, that means that is 0 outside. And we have the same formula here, that this sum is 0 for every, we test for any function in HS0, but the equality must be true for any V and almost every T in the interval. Then here also, we don't need to test with function that depend on T. We can just test with function that does not depend on T. But if you want to test with function that depend on T, you integrate, you will get another formula, but all those two are also equivalent. Here also we have existence. One can prove that there exists for, if you give me Z, that is H1 with value in HS of the complement, I can always find a unique solution, and I have continuous dependence of solution with respect to the data Z. To give you an idea, is only that, like I said, since omega has a ellipsis boundary, for any Z, I can extend it to Z tilde, and the extension operator is continuous. That the norm of Z tilde in the full space is less than Z, is a constant times the norm of Z with value in HS of the complement. That is the consequences of the extension. Now also we know that Z tilde in H1 of with value in HS, then we can calculate the fractional Laplacian of Z tilde, and we will be in the space H1 with value in the dual of HS. That is H minus S. And also we have here this continuous dependent, that the fractional Laplacian of the extension is less than the constant times the extension, the norm in Rn. But we know that this extension, we can use this inequality to have a constant, is less than the constant and the norm of Z with value in HS of the complement. Then that's why we can use that to have this continuous dependence of solution with respect to the data Z. Then to do that, let's give you an idea. First, let's assume that Z does not depend on X. If Z does not depend on X, that is the elliptic problem that we have solved yesterday by using the lifting argument. Okay, that we define the solution by extending on Rn and saying in the restriction at the complement in Z, and the Z tilde solve this equation is a weak solution of this equation in the sense that this double integral is 0 for any V in HS0. That is exactly what we showed yesterday. Then that I said the existence of weak solution of this equation was proved yesterday. But now, if we assume that Z depends on T, then we have that Z tilde is with value in HS that we have seen. Then we can use the lifting argument. We let W is U minus Z tilde. Then W is 0 outside. And then you can calculate. You calculate the time derivative of W. You calculate also plus the fractional Laplacian of W. Then you will get that is equal to minus the time derivative of Z tilde. But the time derivative of Z tilde is in L2 with value in HS of Rn. Then we can use what we saw for the first case, that is in L2 here, and then that is here. Then we can use the first case to say that we have a unique solution W. Okay? Then if we have a unique solution W of this problem, then we can say that W plus Z tilde is a solution of our initial problem. Which means the solution of our Cauchy problem with non-zero exterior data. But we can shout this estimate, the estimate 3, 4, then remember that W is 0 outside, then we can use all the previous estimate, the norm of W and the space U0 and U sub 0 are the same, and that is less than the constant time, the time derivative of Z tilde in L2 with value in HS of Rn. And remember that the norm of Z tilde is less than the constant time, the norm of Z with value in HS of the complement. All these estimates that we have done before. And now we just use the triangle inequality. Use the triangle inequality and you get all this estimate. By using the previous estimate and the triangle inequality, you obtain all these estimates here. Now, remember that dt of Z tilde, because Z tilde is nice, that is also a solution of the Dirichlet problem with Z replaced by dt of Z. Then we know that dt of Z tilde is in L2 with value in HS of Rn. Then we can also get that the L2 norm with value in HS of Rn of the derivative is bounded with a constant with the L2 norm of Z, but with value in the complement. Now you combine with the previous estimate, we get exactly the estimate that we want to prove, the continuous dependence with respect to the data of the non-homogeneous equation. Then you can always solve, but for non-homogeneous equation, especially for Dirichlet, you cannot, even for the Laplacian, if you have a non-homogeneous boundary condition, you cannot use directly semi-group method to solve this kind of parabolic equation. Okay? Or for other boundary condition, one can turn around and come back to use some kind of semi-group theory, but it's not, you cannot directly apply it for the Dirichlet. For Dirichlet, you can't. You cannot use semi-group theory. If the given data is nice, you make a lifting argument. If it's not nice, you have to find a way. So for any question, okay, but here it's nice that because we can also give an explicit formula of the solution in terms of the eigenvalues and the eigenfunction of the operator that we have defined. Then if we see lambda n and phi n is, lambda is the eigenvalue of the realization of the fractional Laplacian with Dirichlet, zero Dirichlet exterior condition, and phi n is the associated normalized eigenfunction. Then the solution of the Dirichlet problem that we have is given by this series. Then that is the exterior data, the L2 of the complement, the L2 that is the scalar product that with L, the non-local normal derivative of the eigenfunction. And here is exponential of minus lambda n tau, and you have phi n. Then that is the convolution of those things, of this term with the eigenfunction, the eigenvalue that we get. That is the exact formula of the non-homogeneous Cauchy problem. That is sometimes useful, but here we will not use it, but it's sometimes useful if you want to do controllability of this problem. You can use this explicit formula to try to control our system. Okay, like yesterday, here also we cannot use what we did because our control space is L2, we don't have enough regularity, then all the solution we define, we cannot use it because we lack of regularity. Then we have to use other notion of solution like we did yesterday. Here also we will use what we call the very weak solution or solution by transposition, the same, but here for the parabolic system. Then we need solution when the given data are only L2 integrable, are only square integrable, which means they are only in L2, not better than L2. Then we want here we even not to reduce the regularity not only in space but also in time. Then we give z is in L2 of sigma, which means a function that is in L2 of 0t, a function u in L2 of 0t in Rn, that we'll call it a very weak solution of our state equation if we have this integral is equal to minus z times the normal derivative of v. But we test it for any v in L2 of 0t with value in v, intersection h1 of 0t with value in L2, and remember that that one means that the function is 0 at t. And v is only the domain of the fractional Laplacian with Dirichlet exterior condition. Remember here it is well defined because the function is h1 with value in L2, then dt of v is in L2, v is in the domain of the fractional Laplacian, then this guy is also in L2, then here it makes sense. The z is in L2 of the complement, and we know that if v is in the domain of the fractional Laplacian, also the non-local normal derivative is L2 of sigma. Then everything is well defined. Then if this equality holds, we say that u is a very weak solution of our parabolic problem. But if we want, we can also test here with a test function. We can take only v. If we want, we can take v to be in the space of test function of 0t times omega. We can also take that change in it. Any questions? Okay, then we will use the Lyon's theorem, I just write it here. We will use the Lyon's theorem like yesterday to prove the existence of very weak solution. Like I said yesterday, the Lyon's theorem is not only for elliptic, it's work for any type of equation. We can always use this as long as you have the same structure. Then what we do here, existence, then that is a paper that we had in 2020 with Albir and with Dispanshu, and he's now having a postdoc in Emory University. Then we have z in L2, then we can always prove that there exists a very weak solution u that satisfies this continuous dependence condition, that the norm of u in L2 is less than a constant than the norm of z in L2 of sigma. And also, if z is nice, we can prove that a weak solution is always a very weak solution, and every weak solution is also a very weak solution. Then the proof, I will test it. I take here in the Lyon's theorem, I take phi to be the space of test function. But I do it with the norm L2 of 0 to its value in HS0 of omega with associated scalar product. Then, of course, this embedding is continuous. That is the first condition. I define my bilinear form, and my linear form the bilinear form is exactly what we see in the definition of very weak solution. And the linear form is exactly what we see in the right-hand side there. Then if we elect v to be a test function, then of course the that map u to E of uv is continuous, because you just use here that is the Cauchy-Schwarz inequality that is less than L2 of q times the norm of minus delta A dtv plus minus delta SV in L2 of q. Since v is nice, this guy is finite, then we have that is continuous on L2 of q. Now we do coexivity. We take V to be a nice function. Then E of VV is the integral of V of this. Now you just integrate by part. Remember that V is 0 at capital T, like 0, then everything disappears, and it will get you exactly the L2 norm of V with value in H as 0. Then you have exactly, you will have this estimate. You can even have it with equality if you want, okay? Then we have this coexivity. And using all our previous estimates, you have L of V. Remember that L of V ago. L of V is the integral that Z times the non-local normal derivative. Then L of Z is less than L2 norm of Z in sigma times the L2 norm of the non-local normal derivative. But remember that is a continuous operator from V into H as 0. Then we get here the continuous, that L of V will be a continuous linear operator with respect to the L2 of 0t in H of 0 norm. Then all the conditions of Lyon's theorem are satisfied. Then we have a weak solution. But remember, Lyon's theorem does not give uniqueness if the space capital Phi is not complete. Here we take the space of test function with this norm is not complete, then we have to prove uniqueness. But uniqueness, like always, you suppose you have two solutions, you make the difference and see if the difference is 0. Then here, the difference of two solutions will satisfy this equation that the integral on Q of U times that is 0. For any V, you can take any V in L2 of 0t intersection H1 of 0t with value in L2. But if you remember, when we are solving the Cauchy problem, we know that if you give me any W in L2 of Q, I can find a unique V in this space. That is the solution of this Cauchy problem. Because that is what we call the backward problem. Because the V of capital T is 0. That is not that is the backward problem or the dual problem. Okay, that is satisfies in Q, and here it's already included that V of capital T is 0. Then from that you can get that, oh, okay, then the integral of UW on the cylinder is 0 for any W in L2 of Q. Then the fundamental lemma of the calculus of variation tell you we have a unique solution. Then let me tell you, let's see. Now we have to prove the continuous dependence of solution. Then we have said that the non-local normal derivative of V is in L2. Now if we define the mapping M from L2 of Q to L2 of sigma, then M is linear and continuous, and you can find a constant such that the NS of V norm of L2 is less than C psi here as we define this thing. Then if you remark that you take the integral on Q of U psi, that is exactly the integral of sigma of Z M of psi, and you use this estimate, now you know that is less than the norm of Z in L2 and norm of psi in L2 of Q. Now you divide by the norm of psi in L2 of Q, and you take the supremum over psi in L2 of Q, then you will get that the norm of U is less than the norm of Z in L2 of sigma. Okay, then here you divide and you take the supremum over psi such that you obtain exactly that the norm of U in L2 of Q is less or equal to a constant times the norm of Z in L2 of sigma. Now we come back to our control problem. Then since our state equation, the parabolic equation, is well posed, and we have continuous dependence of solution, we have that our solution map that give me a control, that give the very weak solution. This solution map is linear and continuous. Okay? And here, then our functional G we can change now. Inside of writing thing, we can just write our function and just depend on our control variable. Then capital S of J is the small j times S of Z. S of Z is exactly the U, then plus the penalization term. Then our problem becomes that we want to minimize this functional under the condition that Z is in the set of admissible control. Then here we have the existence. Then if our set of admissible is controlled and convex, subset of ZD, and C psi is positive, with G also greater or equal to 0, or the set of admissible control is bounded, and the J is weakly low or semi-continuous, then we have a minimizer. Also, if we assume that J is convex and psi is positive, or J is strictly convex and psi is greater or equal to 0, then the minimizer is unique. It's only that this condition will give us that the functional that we have is strictly convex, and we know strict convexity always implies uniqueness. Well, let's give an idea of the proof. Like the rest time, because we have that we can always construct a minimizing sequences such that the infimum is equal to the limit of these minimizing sequences. Now the condition given on psi and j, the control of admissible set say that this minimizing sequence is bounded in the space of our control, in the space where they belong to control. But since it's a reflexive Banach space, here is a Hilbert space, we have that a weak convergence to a number, to a function z bar. And of course, the closeness of the set of admissible control say that this limit belongs to the set of admissible control. But you have to now also to show that here that the U bar, this means S of Z bar, and that also satisfies the state equation, and also that Z bar is a minimizer to our control problem. Then also here we have that the minimizing sequence is satisfied here. That is the definition of weak solution, because UN is a very weak solution with given data Zn. Then we have that for any V. Now the weak convergence of UN to U bar and Zn to Z bar, taking the limit, we get that U bar and Z bar satisfy this equality for all V in L2 of 0t with value in V and H1 of 0t with value in L2. And that is exactly the definition that we gave, that U bar is a very weak solution of the parabolic problem with given exterior data Z bar. Then we have that what we find that U bar and Z bar satisfy the given the state equation. Now also here we know that Z bar is a minimizer follow from the weak law of semi-continuity that yesterday, and uniqueness follow from the assumption that we have a strict convexity of our functional. Then the proof is exactly the same. There is nothing to change. It's only the spaces that you consider that change. Otherwise, everything is the same. How to prove that G bar is a minimizer, and also we have uniqueness. Now, we want to give what is the optimality condition for this case, and also here to have optimality condition, you also have to compute what is the adjoint of your solution to state map. Then the solution to state map, what you see is I give my control, I want the state, that is the Z, that is not S of Z is U. Then we need to find what is the adjoint of this one. Then here the adjoint is also given by minus the non-local normal derivative of P. Well, P is the solution of this one, what we call the backward problem, or backward or adjoint problem. Then here is backward in time. Then that is a nice, because if you take P of t minus small t, that one solve your forward problem. Okay, and we know that the forward problem, we already know the regularity. That means that the solution here of the backward problem has the same regularity as the solution of the forward problem. Then its non-local normal derivative exists, and it really belongs to our L2 of z. This means L2 in 0t with value in L2 of the complement. Then how we compute here, we just take the scalar product of W with S of z, that is in LQ. Then that is the dual applied to W, but with z, now in L2 of the complement. Like I say, remember that P is nice, P is here, and the time derivative of P and the fractional Laplacian of P both are in L2 of Q. Then we can test our equation with the SZ, our solution, and you integrate using the notion of very weak solution. Then we get that this scalar product is exactly what we have, minus dt of P plus minus the fractional Laplacian of SP times S of Z. But that is in L2 of Q. Definition of very weak solution say that that is minus Z, the normal derivative in L2 of the complement. And that is the definition, that is Z S star of W. Then you get that S star of W is really given by minus the non-local normal derivative of the solution of the adjoint equation. Now we have here the first order optimality condition, that if we have a minimizer and we assume that G is Fréchet differentiable and the Fréchet derivative at U is in L2 of Q, then the minimizer satisfies this optimality condition. That is the integral on sigma minus here the non-local normal derivative plus psi z bar and z minus z bar, that is non-negative. And of course, P bar is the solution of the backward problem with right-hand side the Fréchet derivative at U bar, at the state U bar. What one can prove that z bar is exactly the projection of psi minus 1 times the non-local normal derivative of the solution of the adjoint equation. Then that the optimality condition that we obtain from this parabolic control problem. Then the proof also goes the same like the elliptic case. And I will stop here. Then if you have any question, we have a little bit time to answer questions today. Okay. Thank you very much.